So today is the 2nd of September. Um, and what we are going to do today is we're going to get into amino acids a little bit more. Um, we are going to spend a good bit of time on amino acids. And the reason for that is they are so foundational to everything about biochemistry. There's lots of fundamentals that are related. So there's that where you can kind of recall information. Um, but the better you know your amino acid structures, the better you understand a protein, and the better you understand an enzyme, the better you understand what's taking place within a cell and different metabolic processes. Now, I know that 4385 is not a mandatory class, and I know many of y'all take 4375 because you're a chemistry major and you need this as an upper division elective. Um, but I'm kind of the belief that 4385 is it's almost like I don't know if you ever took a foreign language course, if you took like the first semester foreign language course but didn't take the second semester foreign language course. That's to me what's similar about biochemistry this class and metabolism 4385. It's kind of like, hey, I'm going to introduce you to lots of different molecules, and then you're going to go and never use them. Whereas if you take metabolism, that's kind of like, hey, I'm going to introduce you to a bunch of different molecules. Then you're going to learn about their synthesis, learn about what they're doing within a cell, what they're doing in a reaction. And the connection between this and a foreign language course is like your first foreign language course, you're learning, you know, how to conjugate a verb. And then the second foreign language course, you're learning about how to read the language. And so it's like conjugating a verb is not particularly helpful, or communicating is, doing that, but not taking the course where you begin looking at the literature is kind of, I don't know, it might be boring. Okay. So last week, what we talked about and kind of ended on was there were a total of five polar charged amino acids. There were two polar negative. Those were aspartic acid and glutamic acid. And then there were three polar positives. Those were arginine, lysine, and histidine. Now, we're going to look at those, and we're going to also look at some of the other amino acids. Now, there were, remember, three major groups of amino acids. There were just a second, your polars, and then you had your polar positives, which were single letter codes, lysine for K, histidine was H, and arginine was R. And then negatives were D and E. These are polar positives. Then there are these six amino acids: serine, asparagine, threonine, glutamine, tyrosine, cysteine. These all have three-letter codes and single-letter codes. SER, S. Threonine is T and THR. Tyrosine is Y and TYR. Asparagine is ASN and N. Glutamine is GLN and Q. Last is cysteine, CYS, and the single letter code of C. Now, I'm going to draw this dividing line right here. That's to separate your polar positive and polar negatives from the polar uncharged. Now, one thing that I want you to remember is that, or actually, I'll ask, does anyone remember the pH at which I draw all of my amino acids? And I recommend, whenever I draw a structure, this is the pH that it's at. 1. It's absolutely right. So what that means is that all of these amino acids on this slide are all drawn at a pH 1. Okay. Now, let's look down at tyrosine down here at the bottom. Okay, so I'm going to start on the left-hand side. Here's our N termini. That N termini is positively charged. Then I'm going to go over on the other side of the backbone to the C termini. That's our COOH. That has no charge whatsoever. Now, question, and add a Y or an N to the chat. Is this group that I'm putting a star by, that I just put a star by and now I'm drawing an arrow to, is this group protonated? Yes, or Y or an N? You're right. It is. Now I'm looking for a numerical answer. This group that is protonated, that I have an arrow point, that the arrows are pointing to, this carboxyl group, what is the charge of that group? Just this group. Just this group. Okay, I'm getting a mixed bag of answers. This group right here is completely neutral. Because let's think about a carboxyl group. O, O, H. Okay, so our carbonyl carbon, sure, that's got a partial positive charge. Now, let's think about it this way. This is our carboxyl group, but tell me about a hydroxyl group. What is the charge on a hydroxyl group? The way that I've got it circled right here. Well, this group right here, and actually I'm getting the way that I've got it drawn right here with the circle around it, I've got a single bond going to an oxygen going to a hydrogen. This oxygen has lone pairs of electrons, totally. But if this hydrogen is here, that group has no charge whatsoever. It has a zero charge. So what people are adding into the chat of -1, let me draw a carboxyl group with a -1 charge. O, O minus. Okay, now I'm going to label these A and B respectively. A and B. Answer with a Y or N to the chat. Are these two groups the same? I mean, are they drawn identically? Do they have the same atoms present? No, they don't. Okay. Now, add the letter to the chat for the group that is protonated. Is it A or is it B or is it both? Okay. A. You're absolutely right. So that means that B is deprotonated. Add a Y or an N to the chat if you would agree with that statement. Okay. So this protonated form that we see for A, this is neutral. So I'm going to write neutral. Then if we look at group B, okay, group B has lost a proton compared to A. Would you agree with that statement? Y or an N? Okay. So it lost a proton, and with it, it lost a positive charge. So if something is neutral and it loses a positive, what is its charge? Add that to the chat. If something is neutral and then it loses a positive, you're absolutely right. It's -1. So A and B here, we've got A as a neutral carbonyl group, and then B or carboxyl group, and then B as a negative carboxyl group. Now, which one of these, A or B, is going to be most abundant in a basic environment, A or B? Totally. B is going to be present in a basic environment. Okay. Now, that's an important detour that I wanted to take, and I'm glad to take. That is the protonated form. A is the protonated form of a carboxyl group. Now I'm going to erase all of this, and I am going to look up at my tyrosine amino acid. So if I'm going to circle just the backbone, just the backbone, the way that I've got it drawn right here. What is the charge on the backbone? Add that to the chat. +1. Spot on. Great job. Now, when I look down at the rest of my molecule, I selected tyrosine because tyrosine is indeed polar and it's an aromatic residue. When you look at the group that is currently circled, we've got a six-membered ring, and then we have a hydroxide group. Now answer with a Y if that group that is circled is protonated, or an N if it is not protonated. Yeah, it's absolutely protonated. Now, follow up to that. Is this group that I have circled? Sure, it's protonated, but my follow-up is, what's the charge on this group? And before you answer, think carefully about, well, look at this group that I've got circled that I'm putting a big X by. Have I denoted a positive on the atom that has a positive charge? I have. I'm not going to play tricks or games with you or anything like that. If a group has a positive charge, I'm going to indicate that with a plus symbol. So now, with that said, I'm going to erase this. Where I've got this arrow pointing, does this group, this whole group, what's the charge of that big group there? Fantastic, 0. I think I saw a +0 or +0 in there. No, I did. +10. No, it's just going to be 0. Okay. Now, with that in mind, we've looked at all the different pieces. Add to the chat, what is the charge of this amino acid? +1. Okay. You're absolutely right. Great job. Now, despite that having an overall charge of +1, tyrosine is an uncharged amino acid. The reason for that is because we don't care about the backbone. We only care about the R group. And this right here is the R group. And at a pH of 1 or a pH of 7, this group has no charge whatsoever. Now I want to introduce you to two other amino acids, asparagine and glutamine. With asparagine and glutamine, let's just take asparagine. Thinking about asparagine, and you can toggle back and forth between any other slides or anything like that, but does the name asparagine, answer a Y or an N? Okay, I just got a private message. Does that apply to any others where we ignore the backbone charge? Every single amino acid, we ignore the backbone. Whenever it comes to classification of amino acids as a polar positive, polar negative, polar uncharged, or a non-polar, we do not care about the backbone. Because if we did, then we would classify every single amino acid basically the same. Okay. Does that address your question? Unidentified student. Okay, great. And I will do my best to always maintain confidentiality. If you send me a private message, I'm not going to be like, oh, Joe Schmo asked this. But you didn't send a private message to have that said. Okay, but I encourage you to ask questions and private questions, whatever, because other people have that same question. Now, okay, what I wanted to do is let's look at asparagine up here. 3-letter code of ASN, single letter code of N. If we look at this R group, and let's just, okay, looking at that whole R group, we've got a carbonyl carbon with an oxygen going to it, and then NH2. Okay, and add to the chat, what pH was this displayed at? Perfect, 1. As acidic as it can possibly get. So let me ask you this. Do you think that this group or that nitrogen right there that I'm pointing to, yeah, this nitrogen right here, do you think that it's going to pick up another proton? Y or N to the chat. This is at a pH of 1. It's tempting to say yes, and I see quite a few folks are saying yes. The answer is, though, no, it's not. So this part of this functional group, or this part of this R group, it is not going to pick up another proton. And one of the reasons for that is, does anyone remember the inductive effect? The inductive effect you talked about in organic chemistry, where it's basically like you have this, long alkyl group or something like that. And the pKa of one group, or the acidity or basicity of one group, can be influenced by adjacent groups. For instance, if we had, let's say, this carboxylic acid. Okay, there's a carboxylic acid. That carboxylic acid has a grand total of 4 carbons. Um, and I'm going to draw another carboxylic acid. The inductive effect is the reason that this group right here and this group right here are acids, but acids of different strengths. So the pKa's of these two groups is going to be different. Now, that's just a little bit of a detour, but my point is that this group right here influences the fact that and contributes to the fact that this group right here, where this nitrogen is, cannot pick up another hydrogen. It cannot pick up a proton. So, long story short, this group right here is uncharged. It has a 0 charge. And what that means is that this group that I've got circled, the only group that I currently have circled right here, it is a non-ionizable R group. Is it polar? Yes. Is it going to pick up a proton? Nope. Is it going to lose a proton? Nope. I always draw my amino acids at a pH of 1. And this amino acid right here, asparagine, and same thing goes with glutamine. These groups are going to look the exact same whether the pH is 1 or 14. Same thing goes with serine and threonine. These are non-ionizable side chains. Now, I want to draw another amino acid. I'm just drawing the R group here. CH2, COOH. Okay, I'm going to put a little check mark by the first carbon in the R group. I'm going to do the same thing to asparagine. Could you add a Y or an N to the chat if you see both of my check marks? And I know that this slide's gotten particularly noisy. Okay, so I got my 2 check marks. And now I'm going to put a second check mark on each of my 2 carbons. Okay, so I've got a check mark on each one of my carbonyl carbons. I'm going to put a check mark by each oxygen. Done. And then what I'm going to do is point out the differences between these 2 R groups. One has a hydroxyl completing that carboxyl group, and the other has NH2. Now, this R group right here that I put a big circle around, now I'm putting an X over that circle. Could anyone add to the chat something to identify that amino acid's R group? You can add the single letter code, the 3-letter code, or the full name. And I'll give you a little bit of a hint. The hint is aspara, ASP, aspartic acid. So where I have my X and then I've got this other amino acid, they're similar in structure, but they're different. Aspartic acid right here where I've got an X, that is D, one of my polar negative amino acids. Then glutamic acid is E, a polar negative amino acid, which looks very, very similar to glutamine. Okay, so what we've talked about so far, what I've introduced to you guys is I've introduced your three polar positive residues, your two polar negative residues. I've introduced the six polar uncharged amino acids, and now what we're going to talk about are non-polar amino acids. Now, in the event that you're like, whoa, 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 I feel like this is getting away from me. What I want you to know is that we're going to finish looking at the different amino acids, identifying each one of them, talking about their side chains and their classification. Then what we're going to do is we're going to go on to using these different amino acids to build a polymer and to look at that polymer. And the building of the polymer is more for the visual of it, but we're going to be going back to this well of looking at all these structures and moving forward, coming back, going forward, coming back, going forward. So we're going to look at all these different amino acids in a couple of different ways as we work through this. And on Thursday, I've largely got Thursday reserved to look at building those polymers to see what they look like. So in the event that you're right now thinking, okay, how do I organize all this information in my head? I hope that today and Thursday will be a worthwhile and helpful time for you to do that. So with that, does anyone have any questions before I go on to the next slide, which is our non-polar amino acids? And you're welcome to ask me in a private message or as a whole group, or unmute yourself and ask. Okay. Well, then I'm going to go ahead and proceed. And if you're typing a question, finish. Go for it. Oh, I got a private message of what was E? E is glutamic acid. E is the single letter code for glutamic acid, which glutamic acid has the three-letter code of GLU. Okay, now on the left-hand side of this slide, I've got all 9 of our non-polar amino acids. Absolutely. On the right-hand side of this slide, I've got, oh boy, I got quite a few. Do we need to memorize the symbols? Yes, I'll need you to know the 3-letter codes and the 1-letter codes, as well as be able to use those structures. So just so you guys know, I'm happy that you asked this so then I can state it explicitly. I want you to know the following things. Full name. What does ASP mean or refer to? It seems like a short way of referencing aspartic acid. Nope, that's it. ASP is aspartic acid. That is the 3-letter code. So 3-letter code, 1-letter code, structure. Okay. I want you to, if I gave you the full name of an amino acid, I want you to be able to convert that or translate that to the 3-letter code. Full name to the 1-letter code. Full name to the structure of the amino acid. If I gave you the 3-letter code, I want you to go to the full name. 3-letter code to the 1-letter code. 3-letter code to the structure. I want these to be interchangeable. If I gave you just the structure, I want you to be able to look to know the 1-letter, 3-letter, and the full name. I want you to be able to go back and forth on these pathways. So if I gave you the 1-letter code, you might expect to see a question of what is the 3-letter code for this amino acid based on the 1-letter code? And maybe even see like a multiple choice question that is, which is the correct pairing. And I'd give you a one-letter code, N, and a three-letter code, ASP, D, ASN, D, ASP, and N, GLN, GLM. I'd want you to be able to say, okay, well, based on these, which is the correct pairing? Well, is N paired up? Is N the one-letter code for the amino acid with the three-letter code of ASP? No, it's not. Is D correct for ASN? No, it's not. Is D correct for ASP? Yes, that is correct. N for GLM? No, that is not correct. There's not even something that is GLM. I got a follow-up question. Could you give a tip on how to help remember which ones need to focus on? All of the 20 proteinogenic amino acids that we're covering. So we're kind of doing it gradually. On Thursday, we did our five polar charged. Just now, we covered our six polar uncharged, and now we're going to look at our nine nonpolar. Could everyone give me a Y or an N if they follow? Or, sorry, a Y if they follow, and N if they're... I'm a little confused. What do I need to look at? Okay. All right. So on the left-hand side of this slide, actually, if it's all right with everyone, I'm going to go ahead and clear all my markings here, just so it's a little bit cleaner. On the left-hand side, we have our nine nonpolar amino acids. What that means is that all of these amino acids, they have the identical backbone, but their R groups are non-ionizable. Not only are they non-ionizable, more significant or prominent than that is they're nonpolar. So are these amino acids going to like an aqueous, write an A for aqueous or O for organic? Which environment would they like? Oh yeah, they definitely have a preference for an organic group or an organic environment. But they're not really going to find any protein, or sorry, they're not really going to have the chance for that because proteins in a cell are going to be found in an aqueous environment. Now, I'm going to start at the top here. The top left, which I will zoom in a little bit, is proline. Proline is a ring structure. Proline's R group goes back to its N termini. Proline has the three-letter code of PRO and the single letter code P. Next up is glycine. Whenever I'm looking at my R group, I'm always looking at my alpha carbon. The R group for glycine is simply a hydrogen. Glycine has the three-letter code of GLY and the single letter code of G. Leucine is next. Its R group, it's got this structure. It has the three-letter code of LEU and the single letter code of L. Next up is tryptophan. Tryptophan is one of our three aromatic amino acids, but in addition to being aromatic, it's a nonpolar amino acid. Tryptophan has the three-letter code of TRP with the single letter code of W. Despite the complexity of that R group, it is a non-ionizable R group. On to our next row. The three-letter code is valine, or VAL, for the amino acid valine. This has a single letter code of V. Next up is alanine, which has simply a methyl group for the R group, ALA, and a single letter code of A. The next amino acid, this looks very similar to, that's right, leucine. It is an isomer of leucine, hence the name isoleucine. The three-letter code for this, you might be tempted to say, aha, it's ISO. It is not. It is ILE. Has the single letter code of I. Then our next amino acid, Phenylalanine with a phenol group is single letter code of F, and three-letter code is PHE. Last but not least is methionine. Methionine is one of two amino acids that has sulfur in the R group. There is sulfur, has the three-letter code of MET, and the one-letter code of M. Now, looking at these 9 amino acids, well, not a single one of them has an ionizable R group. All of the R groups are, well, they're uncharged. So all of your polar amino acids are a little bit different from your nonpolar amino acids. All of your nonpolar amino acids only have 2 pKa values. Hence, all of your nonpolars are diprotic. There are 2 ionizable groups, and those 2 ionizable groups are the N-termini and the C-termini of the backbone. Now, when you look at this list over here on the right-hand side, these are all of the pKa's for all of the different amino acids that are diprotic. If you look at the single letter codes, and this is something that you should expect to see on an exam, this information will be provided for you. I'm never going to ask you to memorize a pKa value. The only thing that I will ask you to do or know is that your pKa values are going to be, well, around 9 or around 2. Now, given this list, column A and column B, which one corresponds to the C termini of your backbone? Add it to the chat. You're absolutely right. B. These are all around 2. A carboxyl group has a pKa around 2 on an amino acid. Now, if I look at this list, I could go ahead and scribble out some that are not, or that are polar amino acids. For instance, there's asparagine, there's glutamine, then we've got serine and threonine. What will be provided for you on the test is I will give you a chart that looks like this. So with that in mind, you could look at this chart and say, oh, okay, well, I will be provided with the single letter codes. But I'm not going to say, this chart will not have a column that is alanine, comma, A. Instead, it's just going to be A, C, D, E, F, and so on. Does that make sense? Add a Y or an N to the chat if you understand that. Okay. So almost this exact chart, expect to see that on your exam. Okay. Now, add a Y or an N. A Y if you agree with the statement that every non-polar amino acid, everyone's shown here, has a charge of +1 at a pH of 1. Yeah. Because the only group that is protonated and gives a positive charge is the N-termini. The C-termini is neutral. The R group has no charge whatsoever because they're non-polar. Now, this is kind of our conclusion of sorts. Now, what we're going to work on today, as well as on Thursday, is looking at these individual amino acids, imagining what pH of an environment they're in, and then assembling them into polymers. I want you, since on your exams, you're not going to be expected to draw anything, you have to be able to recognize these. So that is something that you could use as kind of like a guide for preparing for the exam and preparing for quizzes and whatnot. Which, speaking of, your quiz Your first quiz will be posted on Thursday, as will your first homework assignment. Okay. Now, these are our 9 nonpolar amino acids. So to take stock of everything, we've got 5 polar charged amino acids. We've got 6 polar uncharged. So if you account for your polar charged and polar uncharged, that's 11 amino acids. Add back these 9 nonpolar amino acids, and we're at a grand total of 20 amino acids. Are we still doing polls for attendance? We are. Today is one of those days where it's just going to be a freebie, but we will be doing polls. And are we still doing? We're only on day 3. I haven't given up on them that quickly. Okay. So, with or in addition to these groups, remember, we've got our aromatic amino acids, tryptophan, phenylalanine, and tyrosine. Those 3. So your aromatics, they kind of have this like, if you think about it like a Venn diagram, well, an amino acid is both aromatic, or some amino acids are both aromatics and they're polar. Tyrosine being that aromatic as well as polar. Um, and then tryptophan and phenylalanine are your non-polar aromatics. I apologize for yawning. Okay. Now, knowing the structures is important. Knowing the 3-letter, 1-letter, and full names are all very important. But maybe more important than anything else is applying this information. And with that applying or with that application, that's where pKa's are particularly important. If you look over here, you see a chart. The first column is your single letter codes. C, D, E, H, K, R, Y. The next column is your pKa's for your N termini. The next is your pKa for your carboxy termini. And last but not least is your pKa for your R groups. Okay, now with these 4 columns, our amino acid code, and then N termini, C termini, and R group. This chart on the left-hand side shows us which amino acids are triprotic, meaning they have 3 ionizable groups. So let's take a minute and add these up. 1, 2, 3, 4, 5, 6, 7. Okay, 7. Those single letter codes for cysteine, aspartic acid, glutamic acid, histidine, lysine, arginine, tyrosine. Then we've got, I'm just going to take off from 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Okay, 20. Now add to the chat Y or an N. Are there any amino acids that are both diprotic, or sorry, are there any amino acid single letter codes that are on this chart and that are on this chart? Add a Y or an N to the chat. No, there aren't. Okay. How many proteinogenic amino acids are we talking about total? 20. So we got 7 on this chart and then 13 on this chart. 7 plus 13, does that equal 20? Add a Y or an N to the chat. Okay, cool. So would you agree with the statement? Add a 1 if you agree, a 2 if you disagree. Would you agree with the statement that the 20 proteinogenic amino acids that we are talking about are diprotic or they're triprotic? 1 if you agree, a 2 if you disagree. Or a Y works as well. I just wanted to mix it up a little bit. Yes, you're absolutely right. Now I got a follow-up question of, so will you get both of these charts for the exams? Yes, you will. Okay, so now my question for you guys that I'd like you to answer is, how many monoprotic amino acids are there? Zero. Um, how many tetraprotic proteinogenic amino acids are there? Zero. You're absolutely right. Every proteinogenic amino acid is either diprotic or it's triprotic. I'm going to give you both of these charts on your exam, so you'll have them. Now, this is valuable, and we're about to kind of crack open why. Well, I mean, because it tells you the ionizability and whether or not a group is ionizable, but we're going to go through drawing these molecules. Now, this all feeds into protein structure. If you've taken like an intro biology class, it's possible that you talked about protein structure and the different levels. There's the primary, so the lowest level, and that lowest level is nothing but your amino acid sequence. We read protein sequences or peptide sequences from the N termini to the C termini. So if you look at our amino acids in the way that I've drawn these, we read from left to right. So the N termini to the C termini. Now, your primary structure, read from the N termini to the C termini, is also known as your sequence, your AA sequence. This is stabilized by a peptide bond. If you've ever heard of a peptide bond, this is an example of a covalent bond. So I'm going to draw an arrow, an example of a covalent bond. How can you differentiate which chart is for diprotic and triprotic? That's a great question. And the answer to that question is, well, this chart right here. How many pKa values do each of these have? They each have 2. Hence, diprotic. I hope that helps. Okay. Now, typically, whenever somebody is listing the sequence of a peptide, they're going to use the 1-letter or 3-letter code for labeling that molecule. So ARK, for example, this is a short peptide composed of alanine, peptide bound to arginine, which has a peptide bond that links it to lysine, ARK. This is what is known as, because it has 3 amino acids, this is known as a tripeptide. The primary structure is the amino acid sequence, which is kind of what I already mentioned. A peptide, or anything less than 50 amino acids, a peptide is anything less than 50 amino acids, whereas a protein is anything larger than that. So when you talk about proteins, like collagen, for instance, that is more than 50 amino acids making up that sequence. So this is kind of our definition. If I look at ARK, LAMSFLA, okay? Sorry, that was an OK rather than the letter K. This is a peptide that the N-terminal amino acid is alanine. The C-terminal amino acid is also alanine. What connects the A and the R together is this right here, a peptide bond. The R groups are kind of free floating. They're outside of that molecule. Now, those R groups, how would we classify alanine? It's a nonpolar amino acid. How would we classify arginine? Well, that's a polar positive. These groups will interact with different things. That's one of the important parts about protein structure. We need to know about the intramolecular interactions that take place between different R groups. when it comes to bonding, what we are interested in is your valence electrons, your outermost electrons. So how are those electrons available? Well, a polar covalent interaction, we have one atom that has electrons or that wants electrons more than the other. And these atoms are not sharing them equally. So they connect C and N termini of another amino acid. Yes, that's absolutely right. I got a private message that asked, so they always connect C and N. Yes. So the C termini of our, we'll say, first amino acid, this is our C termini, has a peptide bond to the N termini of our second amino acid. That's a fantastic question, and that's absolutely right. So now this right here, this group right here, could form a peptide bond with the N termini of another amino acid. So we have these groups that are constantly available to interact and react with one another. So in addition to our interactions, our polar covalent, there's also non-polar covalent and ionic interactions. Your ionic interactions are going to be, well, polar positive amino acids interacting with a polar negative. Now, it's important to think about all this, but bring along the context that you already know. Sodium chloride, that's an ion-ion interaction. How strong is that? Well, it's pretty darn strong. Is it as strong as a covalent bond? Potentially, but not always. What about an ion-dipole interaction? Well, that's certainly weaker than an ion-ion interaction. Some of them are strong, but when you're dealing with partial charges, it's kind of an imitation of an ion-ion interaction. Hydrogen bonding. Ooh, hydrogen bonding, not super strong, but when you think about water, for example, what gives water its extreme surface tension and extreme high physical properties like boiling point and melting point? Hydrogen bonding. That hydrogen bonding network gives it this unique property because the number of those interactions. Now, to talk specifically about a peptide bond, the peptide bond is resonance stabilized. The way that I will always draw a peptide bond is like this right here. Now, anytime you're looking at a peptide, it's always important to figure out, okay, where is my peptide? Where is my peptide bond? One of your classmates asked about which are the atoms that are bound together. Well, a carbon on the left going to a nitrogen on the right. So this right here, which I'm going to label A, that is a peptide bond. That binds our carbonyl end of one amino acid to the amino end of another amino acid. This is resonance stabilized. This peptide bond will not have a full-on positive or a full-on negative charge. It is going to have partial charges, but it does not have a full-on double bond property, but instead it has about 60% double bond character. It is very rigid and it's very inflexible. Now, with that in mind, what we're going to do is a couple of different things. This is one of my kind of like favorite activities when it comes to amino acids and drawing a peptide. I feel like this is very productive when it comes to learning your amino acid structures. It's a good exercise to like put this into your head. So, could anyone add to the chat the sequence of atoms that make up your backbone of an amino acid? I'm looking for 3 letters, reading from left to right and thinking about the different termini. NCC, perfect. So that is where I'm going to start whenever I'm drawing any amino acid or any peptide. Now, before I do that, what I always like to do is I like to think about, I need to know, and what I'm trying to really get going here is I'm trying to do a couple of things. I'm trying to take my knowledge of classification of amino acids, single letter codes, and three-letter codes, and I want to assemble a peptide. Now, what I will do, what I think is helpful to do, is to say, all right, well, I'm going to convert my name is Joel Gray, into a peptide. Okay. Well, I'm fortunate in that if I were to take on this exercise, this is a lot different than my wife when she was not married to me. She said earlier today, "Oh man, it's so great having a short last name." Um, My wife's first name is Catherine, Kathryn, and her maiden last name had 8 letters in it. And every single one of them could be used to make a amino acid. So I'm going to take my name and translate it effectively into single letter code to make a peptide. So if I'm going to do that, I don't have a single letter code for J. I don't have a single letter code for O. I'm going to say my name as a peptide is ELGRAY. Does everyone follow me there? Add a one if you do, and a two if you don't follow what we're about to do. Okay. So this, thinking about this as a process, the first thing that I want to do is I want to be able to translate that into three-letter codes. We're going to go to three-letter codes, then full names, and then we're going to draw this molecule. Well, this is glutamic acid, GLU, that is E. Then LEU, that is L. I'm going to erase this. Then GLY, then ARG, then ALA, then TYR for tyrosine. So my name, omitting letters that don't have an identifier, is GLU, LEU, GLY, ARG, ALA, TYR. Could you give me a Y if you follow what we're doing and an N if you got lost? Great. So from this, I'm going to translate it into full names. Glutamic acid. Next is leucine. Next is glycine. Next is arginine. Next is alanine. Then next is tyrosine. Okay. Could you give me a number 3 in the chat if you follow what we're doing? And you're good with this sequence so far. Okay, great. Now what we're going to do is we're going to take this and translate this to the structure of this peptide. This peptide has 6 characters, so that makes it a hexa peptide. Now, with that in mind, I've got 6 different amino acids. They all have the exact same backbone. So what I'm going to do is I'm going to say NCC. NCC. Hope I don't run out of space, so I got to be judicious. C, C, N, C, C. I think I'm good. N, C, C, and N, C, C. Okay, so there's my backbone of this peptide. Now, What I'm going to do is I'm going to draw this at a pH. Actually, let me do one thing. Oh, dang it, I can't do that. I'm going to draw this at a pH of 1. So the first thing that I'm going to do is I'm going to go to my N termini, this side, the left-hand side of my structure, and I'm going to put H3 plus. Okay, so that group is fully protonated and it is charged. Then I'm going to go over to the C termini. I'm going to put double bonded oxygen for my carbonyl oxygen, and then OH. Okay, so there's the C termini. Now, in between, there's quite a bit that I have to do. What I'm going to do after this is go to each one of my alpha carbons. And for each one of my alpha carbons, I'm going to put, we look back at, let's take this right here. My alpha carbons. I'm not going to worry about my R groups right now, but I'm going to put this hydrogen on each one of my alpha carbons. So follow me along as I do that. Alpha carbon, hydrogen. Alpha carbon, hydrogen. And the way that I'm identifying my alpha carbons is I'm finding each hydrogen and I'm looking at, well, which is the immediate carbon that follows that? So here's my third nitrogen, alpha carbon, fourth nitrogen, alpha carbon, fifth nitrogen, alpha carbon, and sixth a hydrogen on that alpha carbon. Okay, can you give me a Y or an N? Y if you're good, N if, wait, how'd we do that? Okay. My objective right here is just to complete the backbone of my peptide. Now, the next thing that I'm going to do is I'm going to go to each one of my carbons that are involved in my peptide bond. And what I mentioned a little bit ago, right here, in fact, was I said that I will always draw my peptide bonds with this kind of configuration. So what that means is that if this is my alpha carbon right here, then to the right of each alpha carbon, I'm going to put a carbonyl or a double bonded oxygen. So now I'm going to take that and translate it over to here. There's a double bonded oxygen, double bonded oxygen, double bonded oxygen, double bonded oxygen, da 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 da, and done. Okay, so I've accounted for almost everything. The only thing that is left is my N termini of each of my amino acids. So I need to put a hydrogen on each one of my amino acids, each one of my nitrogens of individual amino acids. So this nitrogen right here is accounted for. This one right here, and put an H. 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 Last but not least is H. Okay, now I've got two questions. My first question is, do you follow this? And my second question is, do I have any charges that I need to account for on my peptide bond? So if you follow this, add a 1 to the chat. If you don't, add a 2. And now so what I was doing there was I was just going through and basically satisfying each one of the atoms within my peptide bond. I took care of my carbonyl carbon. I put the double bonded oxygen on each one of those, and then I had my nitrogen that needed an H. Now, my follow-up question for that is, do I need any charges on any of those atoms? And I mean full-on charges. If yes, add a Y. If no, add an N. You're absolutely right. Those groups, none of those atoms are charged. Because let's think back for a second, or let's go back for a second. This peptide bond right here, where I'm putting an X, it's resonance stabilized. And here are our two resonance structures. A resonance structure is simply an average. It's all of the possible permutations, but divided by the number of permutations. Well, this is one configuration, but this is also a configuration. Due to the fact that it has two different configurations, that does not mean that this is the most important and most true one. What I'm going to do is I'm going to draw it like this because, well, it's not going to have that permanent positive charge. Instead, it's going to have partial charges, for instance, a partial positive here, a partial negative here, a partial positive here, or partial negative here. It will have those, but it's not going to be uh, it's not persistent enough for them to be that important. Okay, so now I've got my backbone. What I want to do here is I want to go to underline my alpha carbons because that is where I'm going to be drawing my R groups from. Now, the important thing is that I'm going to be drawing these R groups at a pH of 1. So if it is ionizable, it's going to be completely protonated. Now, looking back, glutamic acid, leucine, glycine, arginine, alanine, tyrosine. Glutamic acid, the classification is as a polar negative amino acid. Leucine, nonpolar. Glycine, nonpolar. Arginine, polar positive. So we've got glutamic acid, polar negative, arginine, polar positive. Alanine, nonpolar. Tyrosine. Tyrosine is a polar uncharged amino acid. Now, before I start drawing any structures for my R groups, does anyone have any questions about the backbone? And you can add it to the chat as a private message or as a general public message. Okay. So the next thing that we're going to do, and if you're still typing, just go ahead and type. Glutamic acid. I'm going to jump back. Let's find glutamic acid. Do I have glutamic acid on here? Ooh, got glutamic acid. But I can fix it real quick. I think I got that on there. Yeah, there we go. I'll grab it from day 2. What happens to the H's on N during peptide bonds? Okay, so the hydrogen that's there that I left in each one of them, that's going to remain there. However, the peptide bond formation is what you're asking about, and that is a fantastic question. When it comes to peptide bond formation, sorry, just one second. That is what's known as a condensation reaction. So we do have the formation of water between this NH3 and the COOH. Okay, sorry about that, folks. Okay, so I've got aspartic acid right here. And on the right-hand side, I'm going to draw this R group on the previous slide. Right here. So CH2, COOH. And now I'm a doofus because I realized I copied aspartic acid, not glutamic acid. But with aspartic acid, well, glutamic acid is just one CH2 longer. In the slide, the first carbon has 2 hydrogens. However, in our backbone, we only drew 1. Is it just assumed that it has 2, or do we not draw 1? Which slide are you talking about? So this right here, I presume that you're talking about this one. And then peptide bond slide. This slide? Okay. The nitrogen, that's only one hydrogen. This nitrogen only has one hydrogen as well. The carbon. This carbon right here, this is our alpha carbon. Is that what you're talking about? Okay, so that's a great question. It's going to have a hydrogen and an R group. Hydrogen and an R group. What I'm about to draw are all of the R groups. Thank you for asking that question. Does that answer make sense? No, no. Thank you for asking. So, okay, cool. Okay, so as a result, like this carbon right here, this is our first alpha carbon. That now has two groups bound to it. You good there? Okay, awesome. So we've got our glutamic acid. Next up is leucine. I'm going to jump back a couple of slides to find what leucine looks like. Ah, here is leucine. What I need is I need this group right here. I'm going to redraw that. That is my R group, and that looks like this. CH2, CH, CH3, CH3. Okay, so now I'll go up here. CH2, then CH, and then we've got these two methyl groups, CH3, CH3. Glutamic acid's accounted for. Leucine's accounted for. So I got EL. Then after that, glycine. Well, glycine on our alpha carbon has two hydrogens. We've already drawn one, and glycine is the smallest amino acid because its R group is just a hydrogen. So now I'm going to draw here, just a hydrogen. Okay, so now I've got ELG. Could everyone add a one to the chat if they follow if they see ELG here, or if they understand what I'm talking about when I say ELG, and a two if you do not follow. Okay, great. So next up is I need arginine. Well, I went ahead and I copied arginine from the other slide. It's three CH2s and then this funky group. So I'm going to go ahead and I'm going to simplify this for myself because I have handwriting that's all over the place. I'm going to say CH2. I'm going to put that in parentheses. I'm going to put a 3. Then I'm going to go NH, then C, N, N. And what do we got here? We got 2 to give us a positive charge, NH2 plus, and then NH2. This is a functional group that is resonance stabilized. It will have a positive 1 charge. This is all drawn, again, at pH of 1. So now I've got ELGR. Alanine. Alanine is usually everyone's second favorite amino acid. Everyone's first favorite amino acid is glycine because the R group is just the hydrogen right there. Alanine, the R group, is the second smallest, and it is simply a methyl group. So now I've got alanine, which is CH3. And then last but not least is tyrosine. And this is where I want to use a mnemonic to help you remember tyrosine. It's got CH2, then it's got this benzyl ring and OH. Tyrosine. There we go. Now, with all of that said, this is this peptide drawn at a pH of 1. Everywhere that a proton can go, it's there. Now, what could you give me a not accounting for whether or not you've memorized your structures of amino acids, but on a scale from 1 to 5, how would you rank your understanding of how to do this, with 1 being I follow it all, and if I can pull the structures, I'm golden. To 5, I don't even know where to start. 9. Okay. All right. So if anyone added a 4 or higher than that, I would like to help out in any way that I can. Um, with that in mind, this is something that takes time to be able to go through this process right here. Which one thing to recognize is that going from here to here is not trivial. That's translating. I want you to, by the time you take your exam, to be able to go from here to here and back. Then I also want you to be able to look at this right here. Now, like I said, on Thursday, we're going to be doing more of these. Before we proceed or before we call it a day or anything like that, though, I would like you guys to look at this molecule and tell me in the chat what is the charge of this molecule. Okay, I've got a mix of +1s and +2s. Well, what I'm going to do is tell you that it is indeed +2. We've got our N termini. That's a positive charge. Then we've got, let's see, what we want to do is look at the N termini, the C termini, because every single peptide, every single amino acid has an N termini and a C termini with a charge or with no charge. Then we want to look at all of our different R groups. And we'll go one by one. Glutamic acid. How is it classified? It's classified as a polar negative amino acid. In this case, what's its charge? 0. So nothing. Leucine. Oh, that's not ionizable. That's a nonpolar residue. Okay, I got a question. I thought the charge of the backbone didn't matter. Okay, it does in terms of calculating the overall charge, but it does not in terms of accounting for classifying different amino acids. I'm happy that you asked that question. Does my explanation provide clarity at all? Now, one thing that we do not need to account for at all is our peptide bonds. Don't need that, that, that. We don't need to worry about our peptide bonds. And I didn't see a single person look at, I did not see a single person who added up those peptide bonds and said, like, oh, the charge is +12. The peptide bond is irrelevant when it comes to calculating your overall charge. Okay, so now I'm going to go back to the N termini. Positive. R group for glutamic acid, nothing. Leucine, nothing. Glycine, 0 charge. Now, arginine. Oh, that's a positive charge. It's resonance stabilized, but it's still a positive charge. Then, alanine, no charge. Tyrosine, no charge. C termini is no charge as well. Now, all of those different groups, they combine to give us a molecule with a charge of +2. I hope that makes sense. I saw lots of people adding in +2. So great job. Now, with that in mind, do you think that there's a pH at which this molecule could have a charge of +1? Add a Y or an N to the chat. Yeah. What about 0? Add a Y or an N to the chat. Could this molecule ever have a charge of 0? Yeah, probably. Okay, now, So ideally, we just count how many positive signs we have. Yep. Follow-up question to all that. Could this molecule ever charge a +3? No. Oh man, you guys are spot on. That's absolutely right. This molecule can never have a charge of +3. Great job. Great job. Okay. If you can work through this, if you can work through that sequence, constructing the molecule, that is what I need you to do. That's your important takeaway for today. Um, you should be practicing your structures, being able to kind of visualize them and put them together and identify them. I think that drawing them this way, it's a little bit time consuming. It's absolute, no, I'm not going to say it's a little bit. It's absolutely time consuming. I think that it's a good way to study it though. But um, as you work through these structures and as you work through drawing this sort of molecule, it will put you in a better and better place. Um, Now, what we will do on Thursday is we're going to continue on from this. We're going to take the next progressions in all of this. What I think is helpful is to do something like this, to take a name and draw the peptide of it. I mean, it could be a great way to spur your Etsy shop to like say, hey, cool tattoo design, and boom, draw the structure, sell it for 35 cents. Will they always be in pH 1 or will you ask them to draw it in different pHs eventually? I will ask you to tell me, given this molecule, approximately what pH is it displayed at? So I always start at 1 because that is most beneficial to me and from what I've observed over the years teaching this class. Um, let's start and then we'll adjust what this molecule looks like in a stepwise manner. When the pH goes up to 2, how does that affect different groups? Does it affect them all the exact same immediately, or does it affect one and then it affects the other one? So we will get there, and that's something that we're going to tackle on Thursday. Um, but this is I'm happy with this right here as a stopping point. Before I do part ways with you, though, for the day, I'd like to share one very useful resource, and I will add it to the chat. HH HH is the Henderson-Hasselbalch equation, which we're going to get more into that on Thursday and kind of understanding the Henderson-Hasselbalch equation, like its relevance to different structures and everything like that. So we're going to get into that on Thursday. Okay. There's, let's see that one. Yep. This is the one that I want. I'm going to add this to the chat for everyone. Um, Peptide Draw. This is a great resource. And this particular link, if you Google it, PepDraw, you're going to find this one as well as you'll find one housed that under the Tulane University domain. But I like this because then I can type in something like um, star BC. I'll just stop at stars, stare. There we go, stare. And I can adjust some things. For instance, I can say I want to draw this molecule at a pH of 3.5. Draw the peptide, and it will display it. And then I can also go through and I'll say, all right, well, let's draw this. I can get a sense of what it looks like, all the different groups that are protonated or deprotonated. I can say at a pH of 1. Oh, it's changed a little bit. How's it changed? Why has it changed? Essentially on Friday, what we're going to be doing, Thursday, not Friday. On Thursday in class, we're going to be kind of going through this sort of thing, drawing a peptide and looking at how it changes given different pHs. I'm going to stop my share there. Um, But that's what you should expect on Thursday. If you want to practice it between now and then, by all means. Um, the homework and the quiz will both be published on Thursday, so stay tuned. Other than that, though, I hope you guys have a great Tuesday afternoon, and I'm going to stop my recording.